Hello everybody. Today again we are coming up with this fluid lecture. So till now in the previous lectures we have studied about various things like various thermodynamic properties including potential energy, kinetic energy as well in case of fluid. So now in this video we are going to discuss two very short topics that is very important. I mean it's important, right? So let's see what's there. So the first topic that we are going to discuss here is a state relations for gases. Okay, so I guess most of you are aware with the perfect gas law, right, or the ideal gas equation, right? And that is P. Sorry, you have studied in your high school. Okay, PV equal to nRT, right? MRT or nRT. Okay, so if you write, you can write it at P equal to M by V as into RT, and that can be written as P equal to rho into RT. Okay, so this is our ideal gas equation. Okay, so ideal gas equation. Okay, so I mean why we are discussing this, right? This question must come in your mind, like why for any topic when we are studying we should know why we are studying. Okay, so this is we are going to study this because if you see, this is providing relationships between thermodynamic property, right? I will write it simply thermo properties, right? Thermodynamic properties. Okay, and this is only valid for single phase pure substance. Okay, like we have told you in the previous lecture as well, I have told you, like in the whole courses we will only study about single phase pure substances. Okay, there is like only water is there, then only water, I mean liquid water, and if there is a water vapor, then we will only study about water vapor. If something multi-phase things will come, we will use table. We are not going to use any physical relationship or anything, because that is too difficult for multiples. Otherwise anyway we are not going to study those things in this subject. Okay, so like most of you, when we say, like when I told you fluid, so most of you will assume like fluid means water, most of you, and some of you may the second most common fluid that you people are thinking about is air. Okay, that is mixture of gases. Okay, since the mixture of ratios remains constant in the gases, so we can take it as a like a perfect gas. Okay, like a pure substance. Okay, not about perfect gas. So like I mean to tell you, if air is there, why we will take it as like a perfect pure substance? Okay, because this question must come in mind, like this air is like a mixture of something, right? Mixture of some constituents like nitrogen, oxygen and everything, but we will say it pure substance because it the constituents is the ratio of the mixing is always constant. Okay, so that's why we are saying it as a constant substance. Okay, I mean pure substance, constant, that's why we are saying a perfect pure substance. Okay, now let's suppose take air as example. So when we call air as ideal gas, and when we can't call it as a non-ideal gases. Okay, so and when the air is available at I mean higher pressure and lower temperature. Okay, then it can be idealized to ideal gas. Okay, it can be idealized. Okay, idealized to ideal gas. So when ideal gas is valid, we can use this equation there to solve the problem of air related things. Most of cases we take it that much only. Okay, we are not going to use air chart or something to solve this. Okay, and what is this R? So let me explain you everything in the equation. P equal to rho RT. Okay, So most of you know about this because you have studied in your high school. So P is pressure, rho is obviously density, and R is gas constant. Okay, gas constant, and T is your temperature, and it is in absolute term, that means Kelvin. Okay, so let's may discuss quickly about something about gas constant. Okay, so gas constant, that is R. Okay, so gas constant is defined as Cb minus Cr. Okay, sorry, Cp minus Cb. I'm sorry. So all of you know that, right? Cp is the specific heat capacity at constant pressure and the specific heat capacity at constant volume. Okay, and it is its name specifies that gas constant means the value will be always constant. Okay, for a particular gas. Okay, remember that for a particular gas, for a particular ideal gas actually. Okay, we can't define this for any non-ideal gases or non-perfect gas. Okay, ideal gas. Okay, for a particular ideal gas. Okay, now we will quickly discuss about the dimension of R. R, the dimension is, I will write it here. So these questions are important for gate purpose and AC purpose. L square T2 and temperature, what to say, we will get it Kelvin. Okay, so Kelvin minus 1. Okay, this one is the dimension of the specific heat. Okay, and now the gas constant or the specific gas constant, we can define it as R is equal to this one is universal constant and divided by C. I told you here, right? This value is for a particular gases. Okay, so how this will change for a particular gases? So the answer is here. This is known as universal constant. Okay, this is same for every case. Universal constant, and its value is around 8314 joule per kilo mole into Kelvin. Okay, so this is the universal constant values. Okay, and for a particular gas, if you want to get the RS, you have to divide these values 8314 divided by molecular weight of that gas. Okay, so you will get that gas constant. That means for a particular gas you will get the gas constant. Okay, and for example, if we want to take the R of air, I mean the gas constant for air, so we will do what we do, 8314, and the air weight of air is around molecular weight is 28.97, and it will come as 27. Okay, meter square per second square Kelvin. Okay, see the dimension, L square T minus 2 minus Kelvin. Okay, so our we can write it in many of the books. You will see that L square T minus 2 or theta minus 1. Okay, that will depend, the notation will depend everywhere. Okay, so that's what keep in mind, don't get confused here. Okay, so now I hope this one is clear, and you can find it for any of the thing, right? Any of the gases, you will just you will find out the gas constant divided just by taking the universal constant value, that is 8314, and that molecular mass of that gas. Okay, so I hope this one is clear to you. And now let's see something, discuss about CP and CB. Okay, so I've already told you about this statement. See, for a perfect gas or a perfect gas or ideal gas, its internal energy, that is U, is only function of temperature. Okay, so it's actually dependent on temperature, and the internal energy of a perfect gas only depends on temperature. Okay, so this is internal energy, and it only depends on temperature. Okay, and now we want to see that whether CP, CB, how on which parameters this will depend. Okay, how this will varies. Okay, so as all of you know, you have studied in your school days, like the specific heat capacity at constant volume is defined as change in internal energy with respect to temperature at constant density. Okay, and so it's written du, okay, dt, and it is equal to cbt. Okay, that means if you write it as du, as it will written as cb into delta t, right? So now see, this is only a function of temperature, and this is a temperature term, obviously, right? So dB is equal to du by dt. Same thing that I have written here. So now see, this one is temperature dependent only, and this is also temperature dependent only. That means Cv is also a function of temperature only. Okay, right? So we can say that the constant heat capacity, constant volume is also a temperature dependent thing. Okay. Now, in a similar manner, we wish to define Cp as dH by dt. Okay, and at a constant pressure. Okay, and we all know that H equal to U into P divided by rho. Okay, this H is enthalpy, right? Most of you have studied these things here, school days, I mean high school days, 11th and 12th. So I'm not going to discuss this here in much detail. So H, or you may study in your thermodynamics classes. Later we will see if there any courses available regarding thermodynamics. We will discuss in this channel only. Okay, so U Py rho is equal to RT. Okay, so now see, this is only a function of temperature. R is constant, so it's non-dependent on everything, and T is only temperature. That means we can say that H is only function of Ft, right? Temperature function. So now here again we can say that since H is function of H is function of only temperature, that means Cp is also function of temperature only. Okay. Now so we have proved that both. What the conclusion from here we can get is both specific heats are only function of temperature only, right? Okay, so this is our crack of this topic is that the both Cp and Cv is a function of temperature only. Okay, so this one is important actually when you are going to solve the problems. This will play a very big role. Okay, and like we have seen that Cp and Cb are dependent on temperature. Like now the question came up in your mind, like what exactly how they dependent exactly, like if it increase the temperature or decrease the temperature, how the Cp and Cv will vary. Okay, so just for your information, I'm writing here. I'm not going to discuss the proof for all the cases. You will study all these things in your thermodynamic classes. Okay, so for all the gases, Cp and Cb increases on increasing temperature. Okay, so that means whenever you will increase your temperature, the Cp and Cb value will get increased. Okay, for any gases or any air or any kind of thing. Okay, now one more thing that we are going to discuss here is K. Okay, that is ratio of specific heats. Sorry. Oh, ratio of specific heats, that is K. Okay, and how it is defined as K equal to Cp by Cb. Okay, obviously ratio of specific heats. Okay, Cp by Cb, so it's dimensionless quantity, dimensionless. Okay, and its value is always greater than 1. So please remember that, be mindful of this whenever you will solve your problem. Please keep these things in mind, so don't do any mistakes. Okay, so these things are always valid. Okay, so please take care of this. So now we have seen that since Cp is dependent on temperature, Cv is only dependent on temperature, that means K will also only dependent on temperature. Okay, now again the question coming in mind, like how will K varies with temperature. Okay, so unlike Cp and Cb, whenever you increase the temperature, K value of gas gets decreased. Okay, so it's get decreased on increasing temperature, whereas in case of Cv and Cb, it will increase on increasing temperature. Okay, okay, so I hope this is clear to you. And now we are going to discuss another topic. I told you that in this video lecture we are going to see two topics. Okay, so one second topic is there, that is not so important, but yeah, some things that have to be clear about in our mind. Okay, so like we have studied perfect gas law. Okay, so some other question must come in your mind, like is there any perfect liquid law as well available in the world? Like we have seen the straight relationship between thermodynamic properties for the gases. Is there anything available for the liquid? So the answer is no. There is no perfect liquid law, okay, comparable as to that of the gas. So as you know that let me write the topic first. I state relations for liquid. Okay, I state relationship relations for liquid. Okay, so as you all know, liquid is incompressible. I mean the density is almost means constant on increasing pressure and temperature. Okay, it will vary, but it's not so important, not significant, so we are taking it as a constant. Okay, you can watch the previous lecture for more clarity. I've discussed there. Okay, why it's called as incompressible, and for gases why we call as compressible. Okay, we have discussed that. Okay, yeah. Okay, so see, first relation that came up for this liquid is there is no perfect law. Okay, so there is no perfect equation like gases PV equal to rho or something. So some relations that come up in this or liquid gas as well. The first one is, since liquid is comparable, incompressible, sorry, so that means rho will be constant. Okay, so this one is one relation. Okay, and the second relation come up as Cp equal to Cb equal to constant. Okay, so this values remains always constant, unlike these gases. In gases Cp and Cb does not remain constant. Okay, it will vary according to the gases, but in this case this remains constant. According to temperature also this will remain constant. And in case of enthalpy we will write as dH equal to Cp into del T. Okay, these are the three idealized state relations for a liquid. Okay, so I will write it here, idealized state relations. Idealized state relation. So most of these equations you will going to use in your thermodynamic classes, not here, but yeah, whenever we will deal with the temperature we are going to use this. Okay, so don't worry about it. Now like I mean, if you like, if you want to do the problem regarding multi-flow physics, like both liquid and gases are there, then you have to deal with the what to say, table or something. Okay, and now one more thing is that since we have seen these things, okay, and there is no perfect values for all the thing, like there it is something value is given for the R, if you some values are given P, you will get to know R and T from the state relations of the gases. But in this case you will find a table that is for water we are using steam table. Okay, the most generalized table. Okay, and from there you will get all the values. If you know the pressure and temperature, you will get all the values from the table. Okay, there is no such relationship available for the liquid. Okay, so this is the one thing. The density of a liquid usually decreases slightly with temperature and increases moderately with the pressure. Okay, that I have told you, but these are not so significant that we have to worry about that. However, in some cases we have to deal with the very minimal changes, so thereby we have to use a little variation as well. We have to take account of the little variation as well. So first I will write the statement here. Okay, so the density of a liquid will get decreases if you increase the temperature. Okay, okay, and the second is that it will get decreases if you if you get decrease the temperature. Okay, and pressure when you increase the pressure. Okay, this is the relation. If you decrease the temperature, density will get decrease. If you increase the pressure, density will get decrease. Okay, so This is the relation. Just keep in the mind, some question may not maybe come in your gate examination or something kind of thing. Now if we neglect the temperature, I mean temperature is neglected, and you just wanted to see the density variation with pressure, one relation came up, and that relation is P by PA is approximately equal to B plus 1 into rho by rho A to the power n minus B. Okay, and B and n are dimensionless quantity, sorry, dimensionless quantity. Okay, parameter, and this are almost remains constant with respect to pressure and temperature. Okay, so you just take the value for B and T and you will get. Okay, so for example, for water we will take B value as 3000 and n value as 7. Okay, so now let me talk little bit about multiphysics. Okay, I mean multiflow, multiphase, sorry. Okay, so for example, some liquid container is there. This is just for conceptually clarity. If you don't want to see that, just want to solve the problems, then this is not for your purpose. Okay, you will use these things in thermodynamics, so please be aware of that. If you will be clear with this before that, it will be much more easier for you to understand in thermodynamics. Okay, so let's suppose water is filled in this container. Some liquid water is there. This is liquid water, I mean blue one, and this green one is gaseous, I mean steam. Okay, steam is there. Then we have discussed above, like for pure substance, for that I mean perfect gas or perfect liquid, means only if liquid is there or gas is there, then we will say pure substance. Okay, and two phase things like this one, both steam and liquid is present. Okay, steam and liquid both plus. Okay, steam and liquid. In the pure substance, we have seen that two properties are enough to know the state of the liquid. Okay, two properties are enough to know the state of the liquid. In this case, I mean fluid, in this case we need three properties to be known. Okay, like we have seen in this case, if you know the pressure or temperature, you will know the density and everything. In this case, you have to know pressure, temperature, and X means amount of steam in water. Okay, so there can be anything. In case of seawater, you will get here is a salt and here is a water. In case of any other thing, you will get another thing. Okay, in case of pressure and temperature, you can take any two values, like in the above cases, right? The other thing which came in this picture is X. Okay, and all other two things remain same. Okay, so I hope this is clear to you. And some of you are talking in the comment section, some of you have mentioned that, sir, we want to discuss the questions, of previous year of ESE or GATE. So for that we will discuss it after the next lecture. Okay, in the next lecture I will discuss about viscosity and other things, and after that we will discuss the programs. Okay, so till then, keep learning and goodbye.